Hi, welcome to this session at the Italian Virtual User Conference of 2020. In this session I'm going to try to show you how you could improve some of your PowerCLI scripts. This is of course a broad range, and in the allotted time it will be very difficult to show you everything, but if you walk away at the end of this session with just a few ideas how you could improve some of your scripts, I would be very happy. First, a bit about myself. My name is Luc Dekens. I was a system engineer for a European institution until beginning of this year, where I started doing my dolce far niente. In other words, I'm retired since beginning of this year. I've been a PowerCLI user and a PowerShell user since 2007. If you want to reach out to me and ask me questions or contact me for any other things, you can reach me on Twitter. I have a blog with a contact form, and you can ask questions via the VMTN community for PowerCLI. What are we going to do here today? First of all, we're going to have a quick look at why you should try to improve your scripts and how you can do that. At this point, measurement of your scripts is quite important, and I show you a few methods how this can be done. We'll also look at how you can use PowerShell commandlets instead of writing your own lines of code to do certain things. We also will see how you can avoid repetition, in fact doing the same thing over and over again, and condense this in one commandlet with multiple parameters. And of course we will dive into the get view. This thing, you can't avoid it when you're going into bigger scale. If you want to improve your speed of your scripts, you definitely have to look at the get view commandlet. And then we'll close off with some examples how you can optimize your code. And at the end, I'll try to give you some takeaways of what you should have looked at in this session or when you review it later on. Let's start with this first section in the presentation. Why would we try to optimize our scripts? And secondly, how are we going to do that? How do we have objective criteria to know if we actually improved our scripts? On the why, there's first of all the code optimization. You want to improve your code. You have become more proficient in PowerShell, PowerCLI, and the scripts you wrote a year, 2 years ago, you can actually improve them with your new acquired knowledge. Secondly, you can make or try to make your scripts faster, and especially important is when you're using your scripts that you're tested in a relatively smallish environment. You're moving them now to a production environment which has a multitude of objects in there. So your scripts should run as efficient in that big environment as in that smallish environment. Another important reason to do this is when you start sharing your scripts. That could be in the format of sharing a script with your colleagues or with a community, but that could also be when you have a collection of scripts which you turn into functions and now want to publish as a module to the community or even inside your organization. And then there's the point of fixing issues. Some older versions at the time when you wrote your scripts had issues or bugs in there which you worked around in your script. So that's very good, you did a good job there, but in the meantime those issues have been fixed. So you can review your code if you can now write it more optimally by eliminating those bypasses that you included in the past. And there are new features coming in PowerShell, in PowerCLI, but also in the environment in which you are writing your script. A very good example is, for example, the way you call REST APIs. The invoke REST method in version PowerShell 7 has definitely improved compared to what was available in PowerShell 5.1. So you could review that script and use those new features available in PowerShell 7. And of course it's fun to review your scripts and try to optimize them. At least I think it's fun to write your scripts. The opinions here could be a bit different, but after a while you will notice that it is really fun trying to improve your scripts. And when you're doing all that, you'll be a happy panda, and your colleagues and your environment in which you are working will become a very happy environment. Now, after the why, how do we do that? And to have objective criteria to evaluate if you actually improved your script, you have to find a way to measure your scripts. But first of all, there's this option where you can look visually at your script and see which parts you could improve. Now, this requires a certain experience in PowerShell and PowerCLI to just do it with this paper exercise, because you're just looking at the code without actually running it and trying to find improvements. But as you become more proficient in PowerShell and PowerCLI, this is a valid way of looking at your older scripts and seeing where you could improve them. You have learned new ways to write specific things in PowerShell. Try to use that knowledge and see how you can improve your scripts. So you could look at the structure of your script. Did I do everything in a rather sequential way, or did I tackle it modularly? Did I use functions instead of putting everything in one big blob of code? Like I said earlier, there have been language improvements, language features that have been added. Look at those, how you can use those in your existing script. And there have been known issues, bugs, ways or commands that didn't exactly work in the way they were intended to. You had a bypass, well done, but now that issue is perhaps fixed in a newer version. Try to optimize your code with that knowledge. Now, to have an objective criterion to see how you did in improving your script, you have to have a way of measuring your scripts. And what is important, or an important fact in measuring your script, is the total runtime. So how long did it take me, or did it take my script to do this task that I wanted it to do? There are multiple ways of doing that, finding the total runtime. There's the measure command. There is the datetime object that you can use. And there is the .NET object stopwatch that you can use. But this just gives you the total time that your script ran. Sometimes it is quite useful to look at which lines or set of lines are actually consuming most of that runtime. And unfortunately, PowerShell doesn't have at the moment a profiler that allows you to do this work. Now, luckily, to find those hotspots, there is a community module written by Kevin Marquette named Chronometer that does exactly that. It will show you which lines are consuming most of that runtime of your script. And we'll see in an example later on during the demo how you can use this to your advantage. But now it's demo time. Now in this demo we're going to look at some methods that we have to measure how long our scripts run. The first one we're looking at is the measure command, a built-in PowerShell commandlet. And we are running get VM. Now note this is a very small test environment, so the actual time that you will see is of lesser importance. But let's first run this. And we see here that this script, get VM, took 129 milliseconds. Now let's have a look at the next method that we have, which is the chronometer.NET object. So what we do here is we'll create an object, we'll start it, run our commandlet, stop it, and then look at the elapsed time. Now here what we see is that it takes 74 milliseconds. That is quite a difference from what we measured with the measure command earlier. But what is important to know when you're measuring, there is an overhead to most of these commandlets. So if we run this one again, we'll now see that it only took 12 milliseconds. Now this has to do with caching, data already being available, commandlets being loaded and so on. We'll come back on that later. The next method that we're looking at is the time span and the datetime object. So we'll take the time in a datetime object before we run our command. Then we take the time when it's completed and we see what the difference is between those two timestamps. And here we arrive at 28 milliseconds. Now, as we noticed, these times can be very different depending on circumstances in your environment. So what we could do is try to run them all at the same time in succession and see what the differences are. So in this case, we're going to use all three methods and only extract the total milliseconds to see what this gives. Now what we see here is that those times relatively are close together, 21, 12 and 15. So that means that we should have a way of measuring this which eliminates all those discrepancies between single observations. Now what I'm going to do here is run that same test multiple times, 100 times, for each of the three methods that we have. And if we run this, it will take a bit longer. We'll see that the three times that we have now are way closer together than they were with the individual runs. We have 27, 29, 29. So ultimately, which one should we be using here? And to determine that, I'm going to run the test multiple times, 1 to 5 here, so 5 runs, and then plot it in an Excel spreadsheet. Now this takes a bit of time, so I prepared this, and let's just have a look at the resulting spreadsheet. So what you see here is that those lines which represent the total milliseconds are rather close together in a band between, let's say, 35 and 60, which is still quite a delta, but it's reasonable. They all look to be in the same range. So time to take some statistics here. When we take the averages, we'll see that they even come closer together. Now what we can also do is we can take the averages, and this is a statistical method, and throw away the outliers. In this case I'm going to take the average and throw away 20% of the most extreme values. And again, our data is coming quite close together. An important indicator in statistics is to look at the standard deviation. How much do our individual observations differ from each other? And we see that with the measure command and the stopwatch, we have some major differences that are apparently not there when we use the datetime object. And finally, an interesting one also from statistics is to look at the percentile. In this case, I'm looking at the 90% percentile, which means what would be the value to have 90% of our data available under the Gauss curve. And again, here we see that measure command and stopwatch are rather close together, while the datetime one is a bit of an outlier. So to get a bit more a view on what is happening here, I decided to do the same test that we just ran, the big test, compare all three methods, but run it multiple times. So I'm going to run 100 times that getVM, each for the three methods, and then I'm going to do 10 tests each time with an increment of 10. So if you just look at the tests here, what I'm doing is 1 to 10, then I'm multiplying by 10, and each one again will be run, like we see here, 100 times. Now to make this a bit more visual, I'm going to use some Excel module, the import Excel module, which you definitely should have in your tool belt, to produce some meaningful graphs and data. And this runs quite a while, so again I prepared this one, and let's have a look what this brings. So what you see here are the results, the resulting graph, and then those same statistics that I mentioned earlier, except that I used the 80 and the 90% percentile. So what we see here is now we run a lot more tests, that all those values seem to be coming closer and closer together. So this was with 10 runs. Now if we go all the way to 80, even 90 and 100, we see that those values are practically becoming the same. So those averages, for example, they all center around 25.5 and 26. And if we look at the percentile, there again we see that we have rather similar values. So as a conclusion from this is that whatever you use as a measurement method, all three are equally valid. Just make sure that you run it sufficient number of times and throw away the outliers in your runs. And then you come to rather meaningful values that tell you what your average runtime of your script would be. Next, we are going to look at this chronometer module. So let's take a rather straightforward script here. We connect to our VCSA, and then in a loop we 10 times do a get VM, retrieving all the VMs. The actual call to this chronometer module, or to the get chronometer command, is done in this script. We use splitting to pass the parameters. So we have to provide a path where the script that we want to analyze this way can be found. Now if we run this, and this takes a bit since we do this in a loop, we'll see the following results. First of all, we see the total execution time of that script. Then we see line by line how many times each line was called. That's the second column in the beginning of each line. And then we see the time it takes to execute all these lines. So for example, with line 4, we see that it is called 10 times, that's the sleep command. And we sleep for 1 second and the total time is 10 seconds, which sounds reasonable here. The get VM in itself is also called 10 times. Each time it takes 16 milliseconds. Remember, this is an average measured over the total runs. And the total is about 1500 milliseconds. Now let's take a look at a script that is a bit more realistic than the previous ones. This is a rather straightforward script that takes virtual machines and then retrieves a number of statistical metrics from that virtual machine. Afterwards, it will create an object containing all the values that we thus retrieved. So if we run this, you get very straightforward results. Now let's run this with the chronometer and see what is consuming how much time in this script. So what you see immediately here is that line number 14, the one with the get stat, is the line that is in total consuming most of the time that our script runs. We see that it is called 16 times, and each call on average it takes about 53 milliseconds. Now that we know where in our script most of the runtime is spent, we can try to improve our script by concentrating on that specific line. So we notice that the get stat is the most expensive part, so let's try to change that. And instead of doing a get stat for each VM, we're now going to do a get stat for all the VMs in one call, and then use a group object commandlet to split the results up per VM. If we use the chronometer function on this one, we'll see that our get stat is indeed still the most expensive line in our script, but we see that it is only called once for a total of 792 milliseconds. So that's definitely already an improvement. On the other hand, we do see that collecting all those VMs together in line 3 also has a cost. So it's always the matter of weighing cost versus benefit to see where improvements can be made. We can go for a second improvement in that script by using the where method instead of using the where object commandlet. That is important when we create the results where we have to run through all the resulting data and extract the ones that we want for specific properties. So let's have a look at the chronometer values for this run. And we see that we have a slight improvement on using the where method instead of the where object commandlet. So this goes to show that improving your scripts is always a matter of making a small change, measuring what the result is, going back eventually, or continuing on your path of improving your script. In this next session we're going to look at commandlets versus code and repetition. Now, these are quite important concepts in writing scripts. Most of the time it is common sense or using common sense when looking at your scripts and ways how to optimize them. You can ask yourself the question, is it okay to call a specific commandlet in a loop, or should I call it outside the loop and then use other ways of handling all the data that was returned? In that sense, it is always good to look at PowerShell good practices. These are most of the time advices compiled by people who know what they are talking about and they have learned already by experience. On using commandlets instead of your code, make sure that you know about a lot of the basic PowerShell commandlets. They do often things that you would be coding in multiple lines. I'm thinking about grouping with the group object commandlet, measuring, measure object, comparing, compare object, and so on. Now, like I said, it's often a question of wondering what would be the most efficient way to call and assemble my data. Do I do it with one call or many calls in a loop? As we saw in the previous section, you now have a way of measuring that. What is effective? You can see how much time is spent with one method and how much time is spent with the other method. But let's have a look at some code. As an example of avoiding repetition, let's have a look at this script that has the following task. It will look in your environment and try to determine which tags are not used in any tag assignments. To do that, what it does is first collect all the tags in your environment with the getTag commandlet. Then for each tag, it will check if there is a tag assignment using that tag. If there isn't, it will display that, the category and the tag name, and once we have done that for all the tags, we sort the result and display it on screen. Now let's have a look on how we can improve that script. In this script we're going to use a basic PowerShell collection, the hash table, which you see in the first line where we define it. What we're doing here is we're again collecting all the tags, but each tag will now be stored in that hash table. The key into the hash table is the name of the tag. So once we have filled the hash table with all the tags, we will now look at all the tag assignments. And for each tag assignment, we will group those on tag name. This is the use of the commandlet instead of doing code. And for each of these groups, that indicates that the tag has been used. So in that case, we remove that entry from the hash table. And finally, what remains in the hash table are those tags that are not used in any assignments. For that we use the getEnumerator method available on hash tables. And again, we order the result alphanumerically. Now let's have a look how this runs. And as you can see from the result, we get exactly the same result as in the first script. What you also can notice, and I didn't change any fast forward or faster run of the video, that the second script runs a lot faster than the first script. That is primarily because we're using the getTag assignment, which is in itself a very expensive concerning execution time commandlet only once. While in the original script, we used the getTag assignment for each tag in our environment. In the previous example, we showed how you could use a hash table to store data, which allows you to avoid calling the same commandlet every time in a for each loop. Now those hash tables are very useful in most of your scripts. In this example here, we're going to look at data stores. And what we're trying to do is map the LUNs to the data store that is defined on them. So first what we do is we get all the data stores and we filter on only the ones that are shared between the nodes in the cluster. Then we are extracting the LUN that constitute that data store, and in the hash table we store the information of the data store name combined by the canonical name of the LUN. Now in the second part of this script we're now going to run through all the ESXi nodes, and for each ESXi node with an ESXCLI command we're going to list all the devices known on that ESXi node. Now unfortunately that list does not contain the data store name, but with the help of our hash table that we created earlier, we can now easily map LUNs to the data stores on which they are sitting. As you can see here, we now have a useful report mapping canonical names of the LUNs to the data store on which those LUNs are used. A second example using these hash tables is seen here. This in principle is exactly the same script as the previous one, with one difference here. This goes to show how you can use commandlets, in this case again the ESXCLI commandlet, to retrieve information that is not readily available. In the previous list, as you can still see, we had the data store and the canonical name. Now we would also like the LUN number of that LUN in our report. And we do that by using the path list version of the ESXCLI command. Let's have a look. As you can see here, we also included the type, and we have the LUN number for each LUN in our report. Now, since we can easily retrieve the LUN number, we can go further with this. We could, for example, map LUNs that need to be shared between different nodes in an ESXi, in a cluster, and check if each LUN is visible on all nodes in the cluster. So this script is a bit more extensive than the one we saw before, but what it's doing is basically the following. We're again running through all the ESXi nodes in the cluster. Notice at the beginning that we're using two hash tables. You'll see immediately why that is. So in the first part, and that is the basic part that we did in the earlier scripts, we're going to list all the LUNs on each ESXi node. We are storing that in the hash table, but this time we're not storing a single value on the value part. We are storing a complete object in there. And that object contains a lot of the other information we're later going to use in our final report. So first we retrieve all the LUNs, and we prepare the hash table where the key is the canonical name in this case, combined with the UUID of the ESXi node. This to obtain a unique key into the hash table. Now in the second part we're going to look at all the data stores. And what we're doing here for the data stores, we are retrieving what LUNs constitute that data store, and we're going to add that information to the object that we created earlier in our hash table. Now VMFS data stores and vSAN data stores have a different way of showing you which LUNs are being used. That is why we have the switch case here with all the possible options of types that we can have. At the moment, since it doesn't make much sense, this report does not include NFS data stores because they are basically not using LUNs in the sense that VMFS and vSAN data stores are using those. And finally, in that same cluster, we will now look at all the RDM disks that are available there. So we're looking at all the VMs in the cluster on that ESXi node, and then we are retrieving the hard disks that are either raw physical or raw virtual. And again, we are adding that information to the existing object inside our hash table. So now we have collected all that information in our hash table. We can prepare our report. So again we use this getEnumerator method, and we are now starting to group here. We are going to first collect all the ESXi nodes, and you see in a minute why we do that. And then we collect the information from the RDMs and the vSANs and the data stores. And finally, what we do is once we have our final result, we're going to show this in a grid view. Let's have a look what this returns. Now in the grid view, and that is why we were using the ESXi hash table, we created a column for each ESXi node in the cluster. Now if we sort again on the canonical names, you can see that, for example, this LUN here, which is represented by LUN number 3, is visible on all 3 ESXi nodes. So that is a handy way to see if your LUN zoning, LUN mapping is correct all over your cluster. What it also contains is, and this is not available through VMFS type data stores but only vSAN, we're looking at what each LUN is used for in the vSAN setup. So we'll see what type of LUN it is. It could be flash or a hard disk, and if it is used as caching medium or capacity medium. So as you can see, by using these hash tables, we were able to collect a lot of information from different sources and combine them in one final report using those hash tables. In this section, we're going to have a quick look at the getView commandlet. First, getView commandlet returns objects that are also or most of the time available through the extension data property on most objects returned by PowerCLI commandlets. Basically what it gives you is access to vSphere objects. In contrast, the objects returned by PowerCLI commandlets, the so-called net objects, they give you access to properties and methods which are a selection made by the PowerCLI team. vSphere objects, they contain everything that is described in the API reference. A question I get asked quite often is, should I use getView all the time? And my answer is definitely no. You should only use them when you actually require it. Now, when do you require it? Most of the time these are faster. So when you have time-critical scripts, it is worth your while to have a look if getView would solve that requirement. Now, on the other hand, most recent releases of PowerCLI, the commandlets became faster and faster and are now nearing the execution time of getView and the methods available on those objects. Where it is still quite important is when you're running your scripts in large environments, the so-called scaling factor. When there's a lot of objects available in your environment, most of the time it is better to use getView in those scripts. Let's have a look at some code. The sample script we're looking at here is a rather straightforward script. We're looking at a cluster, retrieve all the VMs, retrieve all the hard disks, and then display information about this. So as you can see here, we have all that data available in our report. Now if you want to use this with getView, your script by definition normally becomes a bit bigger. What I'm doing here is, first of all, we're using splitting, which allows us to combine our parameters to all the calls in a bit more readable fashion. But then what we're also doing is we're using the search route. So we limit the scope into which getView is going to look. And we use the property value. With the property value, we're telling getView that it doesn't need to return the complete vSphere object, but only those specific properties that we listed there. And again, when we have that information retrieved, we can run our report. And as you can see, we have exactly the same result as we had before. Now, unfortunately, in a smallish environment, you won't see the difference in execution speed, but trust me, in bigger environments, this becomes quite important. Code optimization is a bit of an art, but luckily it is an art that you can teach yourself, although it might take a bit of time. Also, it is not an exact science. There is no book that will tell you rule by rule what makes your script an optimized script. What you have to do is you have to collect knowledge over time, and that knowledge can come from blogs, come from scripts, modules that you look at, written by others, and by looking at demos even. And it is, like I said earlier, a learning experience. Let's have a look. This is a very common script that most of you probably have run multiple times in their scripting career. It's very straightforward, looks at all the VMs in a cluster, and for each VM it will fetch a metric value, CPU usage average in this case. Now let's just have a look at what error that was. It tells us that for a specific VM the counter could not be fetched. Most of the time that means that the machine, the VM, is or was powered off, but since we're using it real time, it is currently that machine is powered off. Now how can we improve this script and make it more optimized? So first of all, we want to make sure that PowerCLI is installed on the system where we run our script. Think about you're sharing the script with somebody else. Perhaps he doesn't know that PowerCLI is a requirement. Secondly, we have requirements on the version of PowerShell. Why is that? Because we are using a feature on error view here, which is new in PowerShell 7. Then we also start by making the cluster name a parameter that we can pass to the script. That means that our script can now be used for multiple clusters. The person calling it just has to provide a name. We also provide a default. If no cluster name is specified, it will look at all the clusters. Now let's continue. When we don't have an open connection to our VCSA, we send a message and we exit with a specific code. Why is that code important? Suppose this script is called from another script. With this code you can determine actually what went wrong and automate that process. Next, we'll do a try catch. We're fetching the cluster and the VMs. Now suppose that cluster does not exist, or there's a problem in retrieving VMs. With the try catch and a terminating error, we get into the error message here, and again we use a specific exit code, different from the one we've used previously, to allow an external program to determine what went wrong. This is a new version of how errors are displayed on the console, which is specific to version 7 as we saw earlier. We just clean up that variable to make sure that there's no rest of a previous run should that be the case. And then we're going to call our getStat commandlet. But we have splitting in here. So the first thing we do is when we have an error, we're going to bypass that error. We're not going to display anything. But how do we know for which VMs it went wrong? And that is the beauty of this error variable parameter. Also notice that we put a plus in front of the name. That plus means that all errors are accumulated in that variable. It becomes an array, in other words, one entry for each VM for which it went wrong. Now from there on, instead of running, and we saw that earlier, the getStat for each VM, we're going to run the getStat once for all the VMs, and then extract with the group object the data for each specific VM. Once we displayed that, we're going to handle the errors. What we're going to do is we're going to run through that error variable that we defined, and we display the names for which the statistics were not returned. As you can see, this works quite fast, and we have this message at the end of our script telling us which VMs failed on this script. To finish, some takeaways from this session. If your script works, it's a good script. Improvements matter. They can make your script faster or more optimally use the features available. If you want to share scripts, that brings new requirements. And keep on learning and practicing your scripting. Thanks for attending.